Process of RBC formation is a subcategory of hematopoiesis. And to name this, you use as a prefix the technical name for red blood cell with the poiesis behind it, at least part of the name. Erythro. Poiesis. Now, red blood cells, they don't live forever, and they wear out, and they're destroyed. About 1% are destroyed per day. And what's really amazing is that as you're sitting here right now, you are losing and probably creating, if you're in balance. If you're not, then of course it may differ. About 3 million per second. You got 25 trillion or so in your body, so some die and some are produced, and the rate should be about the same if you're normal. If you go to, like I did up in the mountains, what would be the difference? You're making more than are being destroyed for a while until you reach equilibrium at that altitude, you can have a higher number. About 3 million per second are created and destroyed. How are they destroyed? How are RBCs destroyed? What cells do you think in your body would destroy other cells? And it goes further than this, but basically it's, yeah. Macrophage or macrophage. They are phagocytes, of course. Cell eaters. In the liver, and to a degree in the spleen, and some even in the bone marrow itself. And these old cells, they live about 100 to 120 days. That's their lifespan. They become old and brittle, and these macrophages sense that, and they kill them, destroy them.
It says in the reading that the macrophages recognize it actually before the lysozyme breaks down. Is there like a chemical given off?
It's a chemical process, yeah. Chemotaxis is it draws it, it's coming through. What happens is the red blood cells come through the circulation of your liver, for example, if it's a liver we're talking about, well, most of them are. And they're phagocytes, macrophages, in the vessels of the liver, which then chemically sense those RBCs are ready to go, and they will take them in and digest them. The macrophages take them inside the cells. These little guys are trapped in there. The macrophages release enzymes that dissolve and just liquefy these RBCs. Now, if they break down RBCs, what chemical is in there that's released as a lyse? We use the word lyse, which means to split, to break apart these cells. That's the initial concept. The hemoglobin. And what those phagocytes do is they break down the hemoglobin to its basic parts. They destroy that molecule. And that's one thing we want to talk about is what's the fate of that hemoglobin. But circulating 100 to 120 days, traveling about 700 miles through the circulation, and they get old and brittle. Phagocytes take care of them, digest them, and then break down the hemoglobin. I mean, there are other parts to the RBC. There's about 10% other proteins in there, but the hemoglobin is the main one. And that's the one we want to concentrate on. It's not just hemoglobin, but it largely is. Got all this info? Yep. Good. Let's move to clear out this. Ready to clear? Let's talk about hemoglobin destruction or conversion and recycling. When I say recycling, what I mean is that, yeah, there's some of the hemoglobin we get rid of, but there's a good deal of it that we can reuse. The body, if it can reuse something, will. It doesn't eliminate everything that's waste. It has to recycle some of the stuff here. Now, this time I picked the globin part first, and you know what it would need catabolized. What does that mean, catabolized? Break down. It will be chemically broken down to its basic components. What makes the globin basic, ultimately? We can reuse these and recycle them. For example, to make new hemoglobin. It can be a pool or supply of amino acids to create new hemoglobin. Now the heme is catabolized too. What would be the first blank that you've heard already? An element, a metal that's in the heme. Iron. Now this next molecule you probably never have heard of. It actually has a green color to it. And it becomes part of the bile too, so that's why the biliverdin. Those are the two initial components of the heme. You remember if you remember the picture of the heme, I don't know if you do or not, but that structure you saw over there on the right side, it's what they call a ring molecule. In fact, technically, in biochemistry, they call it a porphyrin ring, because you've got this ring of nitrogens holding the iron in the middle, and then these other carbon parts outside it. So it's kind of a ring molecule. Think of it as a clamshell. And when the macrophages release their enzymes in there that dissolve the hemoglobin, start catalyzing its breakdown, that clamshell opens up, the iron leaves, and the biliverdin is the part that's left. So you've separated the iron from the rest of the organic part there. This iron, as we will see, can be reused. The biliverdin, you don't want to keep that. You want to break it, you got to chemically change it further, but eliminate it from the body, and we're going to see that occur here in just a moment. May I hear you? Can you read this? Biliverdin? That's biliverdin. It's the other part of that. What's the fate of the iron? Well, it's going to be reused. But first, this is not true of every single bit of it, but a good deal of the iron is stored. That which is not used immediately is stored in the liver and spleen. The old spleen is still having part of the blood function. There's two molecules, protein-based molecules. The iron has to be bound to the protein now. By the way, I should have prefaced this by saying that, for the most part, just iron within your body, if it's significant concentrations, is toxic to you. So what your body has to do is couple it with a protein to either store it or transport it. So it is then bound to a protein in the liver or spleen, and there are two of them, ferritin. Does that make sense? FeR refers to iron, okay, ferritin. And this one probably makes no sense to you, but this one's hemosiderin. No, not homosiderin. mention these because in your medical field someday you may see a blood test which will show the levels of these chemicals. You'll see these chemicals again. They're stored. They're not supposed to be circulating in your blood unless, I guess, their concentration is too high or something, to any great degree. They're more storage molecules. For transport, the iron has to be transported from the liver and spleen to the bone marrow where it's to be reduced. So for transport, we use, and this makes a lot of sense too, I think, this name, transfer. That protein